You all for coming. It's the last talk, and even though there's no beer, all of you are here, so that's very good. So my name is Jignesh Shah, and I'm a technologist at Samtec, and Samtec is a high-speed connector company. This thing is... So we are a high-speed connector company. We make electrical and optical connectors all the way, including cables, high-speed twin-ax cables. And today's presentation is about how that can be used to architect 400 gig and 800 gig systems. As soon as it starts showing, I have the presentation on a stick. Can I use someone else's computer? So anyway, in the interest of time, I can literally start with explaining what a twin-ax cable is, right? A copper twin-ax cable basically has two copper conductors that are extruded with a dielectric all around it. So the performance of that is significantly better than PCB materials. The reason is in a PCB material, when you have high-speed differential pair, usually will have it on, say, a layer with a dielectric below it and a ground layer underneath it. And you'll be going through vias and transitions like that, which affect a lot of the performance. In case, if the traces are on the top of the PCB, there's air on top, there's dielectric below, so it is a very extremely lossy signal, especially when you start talking about signals at 56 gig PAM4 or 112 gig PAM4. In case of twin-ax cable, you have these copper conductors with dielectric all around it. So it's completely covered with dielectric, and it has a copper foil that also goes along the dielectric, which is your ground. So it's basically a shielded cable. So this is as good as it gets as far as electrical transmission is concerned. And that's what gives the much better performance. So people have been using shielded cable for a long time outside. Now the technologies come where it can be used inside the box. The performance is good enough, and the size of the cable is small enough that you can actually put it inside the box and make it a viable system designed for 50 gig and 100 gig systems, so 400 gig ports and 800 gig ports.
Keep going.
Yeah. So this technology is nothing new. It's been there. We've been making cables since 2004. So this technology already exists. It's just a matter of adapting it for the network architecture. Oh, stop.
It's kind of cut off.
Oh, OK. Thank you. Thanks, Scott. So we'll be talking a little bit about the conventional architecture, the limitations of it, and then the path to 800G, flyover technology, what it is, and also how that can be used to architect the systems differently. And I'll be giving an example of one of the systems, which is the OCP wedge, but that doesn't limit it just to the OCP wedge. One of the things is in the conventional architecture, it doesn't matter what type it is, every design is like a snowflake. And by what that I mean is, design engineers use the same design methodologies in different designs, but you don't end up using the same sub-assemblies or package designs everywhere. Maybe the components are the same, but the design, you don't end up using the sub-assemblies. And as a result, it's not very scalable. You end up requiring the same design team working on different designs, and there are only so many designs that they can work on. Oh. What happened? Or just keep escape every page down? Oh, OK. OK, and as the data rates are increasing, the PCBs are becoming very lossy, as I just mentioned. In a switch, if you have 250 lanes, 256 lanes, that's 512 differential pairs, all of them going through this high-speed PCB, which are 24 layers, 26 layers, it becomes a really complex problem on how to route all those signals. I'll just keep it, just keep down there. That's what I'm doing, actually. OK. I'll just go with this. The other problem in the conventional architecture is the placement of the thermal components. All of these front panel optics and the ASICs are becoming extremely power hungry. On top of that, for signal integrity reason, we have to keep them very close together. So you're keeping all these hot components right next to each other, and the front panel optics wants to stay less than 70 degrees C, the cooler the better. And the ASIC, which is running at 400, 500 watts, is like a big heater right next to your optics, that's your baby. On top of that, some of the channels require retimers, which are also power hungry. So thermally, it's a complex problem. So both on signal integrity and thermals, it's a challenge. So the conventional architecture, if you look at it, for 400G, it can kind of work, 400 gig per port. 800 gig, that's not going to work, both from a signal integrity and a thermal perspective. Latency is not good. Insertion loss is not good. This is well known, right? System thermals, optic thermals, all of these are problems. Manufacturability, cost, and technology is there. So what's the alternative? So at the keynote, people have been talking about an alternative to, what the heck is this? Yeah, yeah, so you want to go one slide.
All right? No, okay.
Just go one slide up, yeah, that one. Okay.
Go ahead.
Okay, and so the one slide down, please. Yeah. Oh, that's been there. So for co-packaged optics, the 400 gig solution is not there, as in no one's talking about it. It's being talked for 800 gig. So yes, the latency and the insertion losses and the system thermals, as an overall system thermals for co-packaged optics is going to be very good. But the optics thermals is going to be a big challenge. Like we said, optics likes to be less than 70 degrees C. And for co-packaged optics, we are talking about putting all of them on a 70 millimeter or 80 millimeter package substrate right next to the ASIC. That is extremely challenging. We are fighting physics at that point. And then there's the case of manufacturability. People who've been designing optical transceivers know how difficult it is to make multi-channel transceivers. And when multi-channel, it means 8 channels or 16. Out here, we're talking about putting all 256 lanes, which is 512 fibers, or in the case of 51 terabit, 1,024 fibers all on the substrate. One of them goes down, your yield, your manufacturability is shot. That is an extremely difficult problem to solve. And also the technology is not there. People have shown it on small few channels, but to show it on large number of channels and manufacturability is not there. So an alternative to that is what we are proposing is called modular architecture with copper twin-ax cable. Copper twin-ax cable already exists for 400 gig and 800 gig. We're showing that performance in the booth, both at 400 gig and 800 gig. The latency is low because the insertion losses are very low. The system thermals and optic thermals are much better than the conventional architecture. The manufacturability is actually better than the conventional architecture because it's extremely modular design. And the cost and the technology are also very good. The technology exists right now. In fact, it has existed for quite a few years. It's a matter of, it starts to make sense when you go to 400 gig and 800 gig ports. So now people have started looking at that as an alternative to conventional architecture. This is the same slide. Okay. So what is flyover technology? Flyover technology basically is you take a copper twin-ax cable and you connect it on both ends to high-speed connectors. Those high-speed connectors can be any high-speed connector that you would like. So we have a variety of high-speed connectors that we offer. In this case, what we're showing is on the far right, it's a QSFP or a QSFP-DD type connector, so which would accept a standard QSFP or a QSFP-DD optical plug or a DAC cable. And connected on the other end is a variety of N2 connectors depending on what your application is. If it needs to be under a heat sink, it needs to be low profile. If it needs to be between heat sinks, smaller footprint, different types of connectors that you can get. Now, what is it? And this is something that I already talked about while we were getting it set up. So the construction of the twin-ax cable is basically 2 copper conductors with dielectric all around it and a copper foil all the way around. This technology has become small enough that you can put it inside a box. The size of the various gauges available, the gauge that makes sense inside the box for 400 gig and 800 gig ports is the 34 gauge cable. that size is basically less than a millimeter thick. So even though there are a large number of cables, they can fit easily inside a system, inside a switch box. The manufacturing is done in such a way that the two conductors are held very tightly during the extrusion process. And if you had an 85 ohm system or a 100 ohm system, all you have to do is just change the separation between the two conductors while the extrusion is happening. And you will have an 85 ohm cable or a 100 ohm cable or whatever custom. Some people even ask for a 92 ohm cable. So that can be customized very easily. As a result, the cable has very low skew. As a result, the insertion loss of the cables is 4 times lower than that of the best PCB material there is. So best PCB material is Mectron 6, Mectron 7. The insertion loss that you get out of the cables is 4 times lower. So in this graph, the yellow, pink, and the red are PCB materials. Okay, so the red is the Mectron 7. The range that you see, the band of red or pink and yellow that you see is the over temperature performance. That is over temperature, and when you go from 25 degrees C to say 85 degrees C, the insertion loss increases in PCBs. The green and the blue is for the copper twin-ax cables. Not only is the insertion loss very low, but over temperature performance variation is extremely low as well. And that's what makes it a compelling argument. Now, the cable is very good, but in addition to that, so is the connector as compared to the traditional edge card type of connector. On the bottom right, what you just seen a cartoon of what a QSFP-DD or any edge card connector looks like. It has connector pins which have these 90-degree bends, and then they get soldered to the host board. High-speed signals don't like complex bends, just from a reflection or even crosstalk if the pins are very close together. Whereas in the flyover, the image that you see on the far right, the twin-ax cables are directly attached to these contact pins, and which have a straight shot through the back. So as a result, not only is the cable better than the PCB, the connector itself is better than the traditional edge card type of connector. And that gives the even better performance than conventional architecture. On the other end, there are a variety of what we call end-to connectors. We have some which are right angle and horizontal. That's the general two categories. But depending on what footprint, what data rate, what your application, how many lanes you need, a variety of different connectors, all the way from 28 gigabits per second to 112 gigabits per second. The far right says 56 gig, but that's NRZ, so that's good for 112 gig PAM4. In our booth down there, we have a couple of demos. One is a 12.8 terabit switch in which there are 32 ports all running at 400 gig. There are 32 400 gig ports. This is an OCP wedge switch that has been re-architected to show working with flyover. In this one, it has 18 inches of flyover, and because in Europe, that's 450 millimeters of flyover cable. That's longer than what you would need in any inside the box type of application. And it's with a copper loop back to the chip. So it's a complete channel. In that, we are getting bit error rates in the live demo downstairs as good as 1e to the power minus 11 or 1e to the power minus 12 pre-FEC. It's unheard of in this type of switches. If you do a standard architecture, conventional architecture, you would get 1e to the power minus 7 bit error rates for the inside channels, inside ports, and the outside ones, which have a longer trace, you would most likely get 1e to the power minus 3. So this gives us much far superior performance. In addition to that, we also have another demo which is showing 800 gig performance. That means, but that's a single lane, so it's 112 gig PAM4. And that's with the Credo chip. Then there's a bit error rate of 3e to the power minus 7 pre-FEC. Extremely good performance. So if you look at the overall channel budget, I'm showing the one for 400 gig because the channel budget for 800 gig is that's still being debated. It's not. So for the 400 gig ports, the VSR spec is 9.4 dB. That's from the chip to the QSFP-DD, to the front panel optics, is 9.4 dB. With twin-ax cable of 450 meter length, which is longer, like I said, than what you would need, That budget that you get with the twin axe cable type of connector is 6.4 dB. So there's a margin of 3 dB on each side. For your full link, you get a margin of 6 dB. That kind of margin is unheard of in this. And now that you have this margin, you can do something with it. You can either use that margin to run the chips with lower equalization so that power can go low, or someone could decide, hey, maybe I can use a longer DAC cable outside. Instead of a 3-meter DAC cable, I could go to a 4-meter or 4.5-meter DAC cable. That can lead to cost savings. Or I can architect my system differently so that it can help me on my thermals, and we'll talk about that a little bit. So the usual questions now people say is, okay, we get it. Your performance is very good, but you're saying I need 512 cables. I saw that beast of your demo down there. How are you going to fit all of that inside a switch into a 1 RU? Will those cables block airflow? What about thermals? And isn't flyover an expensive solution as compared to traditional connectors? That's where we are proposing a modular architecture. That is, with this, you need to think differently. On the left is a conventional OCP wedge type of design. This is a single PCB, high-speed PCB, 24, 26 layers with 2x1 stacked QSFP DDs, and with the ASIC right next to it. On the right is a modular architecture with flyover. So what we've taken is there's an ASIC module that's pushed further back towards the fans, and in the front are the QSFP DDs. There are 2 reasons to do this. A longer cable is slightly easier to manage than a shorter cable. If you have a very short cable, it becomes a little unwieldy. And the penalty with going with a slightly longer cable, by longer cable I'm saying 12 inches, 15 inches, there is not much penalty in going there because the insertion loss is so low. So the cable management becomes easier. The other is you've taken your ASIC, which is a big thermal load, and pushed it away from the front panel QSFP DD. So your thermal design becomes significantly better. In addition to that, you can have separate modules. So you have an ASIC module, which is made out of a high-speed material. And you have a front panel module, which can be made out of simple FR4, and so can be a COM and power module can be made out of simple FR4. Doing this makes, you can now use your ASIC module in different designs. If you had another switch which had QSFP instead of QSFP DD, you can still use the same ASIC module, just with different cable connectors to QSFP. Or if you had some backplane connectors, we have backplaned XMAX connectors as well, so you can go from the ASIC module to backplane. Regarding cable management, the key in this is to think in 3 dimensions. All system designs until now have been thought in 2 dimensions. So you have a board, because PCBs are 2D. So you just lay out a PCB in 2D. At the most, you might have a mezzanine card, which is another floor on top, but you're not using that volume really well. Whereas because you're using cables, now you can start architecting in 3 dimensions. If you look at it in this image, it looks, oh my God, there are a ton of cables. True, in this view there are. If you were to look from the side, you would hardly see them because the thickness of the cable is that low. The volume of 512 cables is only 1% of the total volume, or less than 1% of the total volume that's available inside a switch. Right? That's the key. That if you can use your volume effectively, you can design a system that can work for thermals as well. And there are multiple cable management options available. We have a demo here where we've shown this is just purely a mechanical demo. Same image that there are a few different cable management options that are available. And we've gone through this exercise quite a few times with customers where we can guide you in how that can be done. Now about thermals. So we've done a complete thermal simulation of a conventional architecture and the modular architecture. And in both these plots, everything is the same in the sense as far as the amount of power, all the assumptions and models are the same. On the left, conventional architecture is a 2x1 stacked. On the right is a belly-to-belly. So now, in general, belly-to-belly optics is much better for thermals than a 2x1 stack. QSFP DD and any of the front panel optics at 400 gig and 800 gig being so power hungry, you need to have the freedom to select what height of heatsink that would work best for your system. So when you go belly to belly, you can do that, and especially in this one, because the front panel module can be placed in height wherever you feel like now. It's not fixed at a certain height. You can put it vertically in any location that makes sense thermally. You can select your heatsink height on both sides to make sense for your system. As a result, the system thermals end up being much better. The ASIC runs cooler, and the variation that you get in your front panel optics is much lower as compared to what variation you get in a standard conventional architecture. Usually in conventional architecture, the ASICs on the outside run cooler, and in the middle run much hotter because the pressure drop through the middle is much higher. The last thing is about cost. Because you've gone modular, the high-speed PCB is 1/4 the size of that of a conventional architecture. And it is fewer layers. The high-speed PCB is only around 16 layers instead of 24 layers or 26 layers. So because it's smaller in size and fewer layers, the high-speed PCB, and a conventional architecture's high-speed PCB is going to be in volume, is going to be around in hundreds of dollars, $800, $1,000, depends on what it is. Out here, so now if you go 1/4 the size, the cost is going to be 1/4. Then fewer layers is going to be even less. And the other PCBs being just FR4, they're significantly cheaper. So there are hundreds of dollars to be saved in PCB cost alone. There's money to be saved in retimers as well. Thermal loads are lower, so there's thermal savings as well. If the system guys can use longer DAC cables, then that savings is huge as compared to using an optical cable. So all of this is more than enough to compensate for the added cost of cables. Forget the DAC cable, just from the inside the box savings from PCBs and retimers is more than enough to offset the price of the cables. As a result, at a competitive cost or lower cost, you get a better electrical performance and a better thermal performance. So it's a complete win-win situation. Typical applications, we've already seen that at 400 gig ports, we are already seeing applications from tier 1 vendors where not all the ports, but half the ports, either the outer half or the top ones, are flyover. At 400 gig, if you have especially multi-chip modules inside, the rows of chips in the further back, there's no way to do this other than flyover. If you try to go through the conventional architecture from a mezzanine card down and under the first row of chips, that's extremely challenging to do from signal integrity. So we're already seeing these applications, it's being deployed now. And at 800 gig ports, we expect this to be all the ports to be flyover. And I've shown the example before was of OCP wedge, but this same can be used for any of the OCP products. If you have any OCP products which has 50 gig and above, 50 gig or 100 gig lanes, the twin-ax cable flyover solution starts to make sense. At 25 gig, you can say, maybe I don't need it. The standard architecture works. At 50 gig and 100 gigs, you should start, I think it starts to make economic and functional sense to use it. There are many different ways to skin the cat. You can modularize in different ways, and depending on what design you're looking at. So in summary, basically, modular architecture is here now. It's already been deployed at 400 gig ports. And as you start looking at 400 gig, 800 gig ports, it will give you a very good performance, thermal, electrical, and cost. It will give you good performance in all three. Thank you. And I apologize for the delay with the technical difficulties, and thanks, Scott, for your laptop.
So we have time for questions, if there are any.
Yeah.
So you mentioned that this technology is actually not a new technology, so I was a little bit surprised. And then why did people didn't deploy this in the past?
So
Did I misunderstand you somewhere?
No. So I did say that, right? So twin-ax cables, for example, we have been making cables, coax and twin-ax cables since 2004. People have been using it in systems for backplane where the cables need to be very long. So because the data rates were low, it made sense where the reach had to be much longer, right? Now as the data rates are increasing, it's starting to make sense for inside the box where the reach is not that long because the standard PCB reaches are not going to cut it. So that's why for inside the box, it's starting to be deployed now. But and this is not, and these are not the only, network systems are not the only places where anywhere if you have autonomous vehicles or any type of embedded systems, it has been being used for quite some time already.
So another question about the cable, right? Is that so in the optical cable, if you have some wind keep on blowing on it, have some instability, that would cause some packet loss. I mean, stability issue.
No, so
will you have the same issue there?
Not at all actually, because first of all, this is copper, so it's a little thicker than and stiffer than fiber, optical fiber. At the same time, it is flexible because the size is that small, and if you go a little longer, it's more flexible. And so we have done all these tests where we have these dynamic loading tests or bend tests. We just have it around a tight mandrel and just going back and forth, so we can share that as well.
So you would think that the band radius of this one is a lot better than the single mode fiber?
The bend radius we can do is 3 millimeters.
3 millimeter. Okay.
Minimum bend radius is 3 millimeters.
Okay.
Yeah.
If it's that simple, how long is it going to take before you can make external DAC cables out of this?
So people are already making external DAC cables, right? We've consciously, Samtec as a company consciously has decided not to go in that market because that's an extremely cost competitive market, right? Right now at 100 gig ports, because our cables are much better in performance than someone else's, it doesn't differentiate. Now when you start going at 400 gig, 800 gig ports, the better cable can start to make sense. So there might be a niche that we might go after. But we are not the only people who do this, right? As in there are others as well who do this, which is good, right? As in you don't want just one company offering this. There are other companies that are offering the same thing. So in an external copper DAC cable, the gauge is a 26 gauge cable. It's much thicker, and that's why they are so stiff. This one is a 34 gauge, so you can, if you come touch it, bend, it's really flexible. So for the type of reach that we are doing, it's 34 gauge is enough.
Just asking for an example, if you would use your switch, how long can a twin-X DAC cable run towards the server, for instance?
So if you look at the oh, you said twin-X DAC cable? Oh, yeah. Yeah, so if you look at this budget that I showed, you have 6 dB of margin. Your 6 dB of margin when you correlate to an outside and you use a 26 gauge, because outside now you can use a 26 gauge cable. So the 6 dB with a 26 gauge cable can help you run 1 to 1.5 meters longer than what you would have otherwise run. So if you're running 3 meters before, you can run 4.5 meters now. But it kind of depends on your total link budget, right? So, but this is based on the VSR specs.
I think there's an example in your booth of a 5-meter cable and the signal integrity of
Right.
that.
And for a backplane, we didn't get it ready in time. We have a backplane of 5 meters that's going to be, so we'll be showing at the one of the next shows as well.
Okay, thank you.
Oh, thank you so
Jignesh.
much.